Hello friends, in this video we'll discuss Favorskii rearrangement. Favorskii rearrangement is one of the important synthetic tool in organic chemistry. The base induced rearrangement of alpha haloketones to carboxylic acid derivative is known as Favorskii rearrangement. Now alpha haloketones simply C double bond O. This is suppose first halogen or alkyl group. The second halogen, if it contains a halogen, that is chlorine, fluorine or such compounds which contains a halogen on alpha carbon atom, in case of ketones can undergo Favorskii rearrangement. Now base induced, that means base is taking part, or it is used as a catalyst. So this is base induced rearrangement to give corresponding derivatives of carboxylic acid. Now these derivatives can be ester, or you can say esters, or even carboxylic acids can be formed after in this rearrangement, specifically ester formation. So that is the product, our final product of this rearrangement. So if we are talking about a straight chain compounds, straight chain alpha haloketones, they can give you derivatives of carboxylic acid. If this Favorskii rearrangement is taking place in case of cyclic structures like this one, double bond O Cl. So this is alpha chlorocyclohexane or cyclohexanone, sorry, alpha chlorocyclohexanone. Now if it is undergoing Favorskii rearrangement in presence of a base like NaOH, it will give, now in this case it will not give you acid derivative, it will give you, in this case it will be an acid, but the most important factor in this case is there is ring contraction by one carbon atom. Now in this case it is starting compound is 6-membered ring. Now the final product is a 5-membered ring. So this is what is this is what happens in case of cyclic structure. There is ring contraction by one carbon atom. So this is cyclopentane carboxylic acid. Now the starting compound for this is a 6-membered ring structure. So this is in short about Favorskii rearrangement, its statement, or this is what is the general structure. Now let's understand the mechanism of this particular rearrangement. First we'll discuss about, this rearrangement can be well understood if we take straight chain compounds. So in case of Favorskii rearrangement, step 1 for mechanism will be, step 1 will be, as we are taking base as a catalyst. So first step is abstraction of proton. So for that, let's see C double bond O. Now see, now this is proton present on alpha carbon atom, and halogen present on alpha carbon atom. So this is R1, R2, R3, R4. This is alpha haloketone, halogen present on alpha carbon atom, and it is a ketone. So this is alpha haloketone. Now this is taking place in presence of a base like NaOH. So first step is abstraction of this proton present on alpha carbon atom. So it loses a proton, and this forms R2 C R1 C double bond O R3, R4 and X. Now carbon atom is more electronegative than hydrogen atom, so while leaving, this proton or this hydrogen leaves back its electron with carbon atom, so this carbon will get a negative charge. So this is what is step 1, abstraction of proton. Now this negatively charged carbanion, it attacks on the neighboring carbon for the purpose of stabilization, as it is unstable. So to stabilize, this carbon attacks on the second alpha carbon present in the same structure. So step 2 is ring formation, or you can say cyclopropanone formation, as it will be a ring of 3 carbon atoms. Cyclopropanone ring formation will be our second step. So this will take place. R2 C minus charge, R1 C double bond O, C, R3, R4 and X. So this carbon will attack on this carbon, so to form a cyclopropane ring structure. So these 3 carbons, this is doubly bonded carbon. Now while formation of a new bond between these 2 carbons, the halogen present on this carbon will be released. Now these two steps take place simultaneously: formation of a new bond between these 2 carbons and breaking of this carbon halogen linkage or halogen bond. And ultimately, while leaving halogen, as it is more electronegative than carbon, so it will take the electron with himself or with itself, and that gives positive charge on this carbon. So this is negative charge on carbon, this will give positive charge on carbon, so they can easily form a new bond between themselves. So this is how cyclopropanone ring formation will take place. This is R3, this is R4, this is R1 and this is R2. These 2 carbon, nothing is remaining. Okay, now this is what is cyclopropanone ring formation, second step. Now step 3 will be, as we are taking part or we are talking about a base catalyzed or base catalyzed rearrangement. Step 3 will be attack of a nucleophile, Now in this case, nucleophile will be anything. It can be a base, it can be alkoxide, it can be hydroxide, anything. So this is our cyclopropanone ring. Now on this, the attack of nucleophile will take place. R1, R2, R3, R4. Now it will be attacked by OR minus. So now this nucleophile will attack on the carbonyl carbon, as this carbon has less electronegative than oxygen. So this oxygen has a delta negative charge, this carbon has delta positive charge. So no doubt the negatively charged will get attracted towards a positive charge, and that is carbonyl carbon. So this coming nucleophile will be get attracted towards carbon atom, or that is carbonyl carbon. So so this addition will take place in this fashion. This is R1, R2, R3, R4 oxygen, and this OR with negative charge on oxygen, as this double bond is converted into a single bond. So this oxygen is now, it has a vacant position. To stabilize this negative charge on oxygen, the ring has to be broken, or this ring gets broken. This negative charge is given back to carbon for a new bond formation, and this carbon will take back its electron from this bond. So this is how this ring will open. Okay, so step 4 is, or after this addition of a nucleophile, the ring will open in such a fashion that carbon R3, R4, this is R2, R1, and this is our C double bond O, OR. This is how it will open. And finally, this will step 4 will be now, due to which this carbon is now its one valency is vacant, so, and it has taken back its electron, so it will have a negative charge. So step 4 will be abstraction of a proton. Abstraction of proton from solvent, no doubt. It will take back one proton from solvent, and this structure is converted into, after addition of a proton, it is converted into R O, C double bond O, C, R2, R1, CH, R3, R4. So this is how, or this is what will form after abstraction of a proton. So there is formation of ester, which is a derivative of carboxylic acid. So this is what is mechanism of this rearrangement, Favorskii rearrangement. So just revise what are the steps in this mechanism. First step is, first there is abstraction of proton from the beta haloketone, alpha haloketone. Further, the negatively charged carbon form a cyclopropanone ring structure, and simultaneously the halogen present on the other carbon atom, it will leave to form such a structure, that is cyclopropanone structure. Now in this structure there is addition of a nucleophile, and this ring will open in such a way that it will have again a carbanion, and this finally this carbanion will accept a proton from solvent to give corresponding derivative of carboxylic acid. Now the important feature of this rearrangement is in which fashion this ring opening will take place. That is the important feature. Let's understand this. Now the feature of this rearrangement is the ring opening, the way the ring will open. We'll discuss that. Now the feature of this rearrangement, for that example, we'll take one example, that is, this is feature. To understand this, let's take one example, HCH3, CH3, C double bond O, CH2, Cl. Yeah. Now, if this is our ketone, first step, it will lose this proton. Second step, this negatively charged carbon will attack on this carbon. So there is formation of cyclopropanone. So I will directly draw the cyclopropanone structure. CH2, C double bond O, because that is important. CH3, CH3. Okay. Now, if this reaction is taking place in presence of an alkoxide like sodium methoxide, so this ion or this nucleophile will attack on this structure, and it will be joined at this carbon. So this is CH3, CH3, CH2, CO minus, and O, CH3. Now, after this ring will open. The electron present on oxygen will be donated to form a new bond between carbon and oxygen, and while doing this, one of these two bonds will be broken, and this is how the ring will open. Now we have to decide, or we have to understand how this ring opening will take place. First way to break this linkage, this is first method or first opening, first choice, and this will be the second choice. Which choice or by which way this ring will open is our point of discussion. Let's understand, or let's make both these steps simultaneously. Suppose this is first way, so this is how. Suppose this bond between these two carbons will break and the ring will open. Now that creates negative charge on this carbon. So the ring opening, after ring opening, this structure will be, it will look like this: CH3, CH3, CH2 and COOCH3 with negative charge on this carbon atom. Second choice is breaking of this linkage. Now after breaking of this bond, negative charge will be on this carbon atom. So let's draw that: CH2 negative charge, C, CH3, CH3 and C double bond O, OCH3. So these are the two choices by which way the ring will open. Now in this case we have to understand the stability of carbanion. If we think about, if we go back, we have earlier in these videos we have discussed the stability of carbocations. Now in this case we have to understand the stability of carbanions, or negatively charged carbons. So which carbocation is more stable? Now if we look, this is a negatively charged carbon. That means one electron is extra, is present on this carbon. Now these alkyl groups, these are electron donors. I am talking about this negatively charged, or this carbanion. These two methyl groups are electron donors, so they will donate their electron. Now these two methyl groups, they are electron donors, and this carbon atom is negatively charged. Due to electron donating nature of these alkyl groups, this carbanion will be unstable, and in this case, as it is a primary carbanion, there is no electron donating group attached to this carbanion. So this primary carbanion will be more stable than this tertiary carbanion. So ring opening will take place by formation of a primary carbanion, not in the fashion, or not by the first choice in which tertiary carbanion is forming. So this product, or this way, the ring opening of cyclopropanone ring will not take place, but it will choose rather this method or this way of ring opening. So this is the important feature of this particular rearrangement, that is opening of cyclopropanone ring. The cyclopropanone ring will open in the same in the format, or in the way it will give a stable carbanion. So as far as carbanions are concerned, primary carbanion is more stable than secondary carbanion, than tertiary carbanion. So this stability order is in the exactly opposite, or in exactly reverse way as that of we have seen in the earlier videos of carbocations. As far as carbocations are concerned, tertiary carbocation is more stable, but as far as carbanions are concerned, primary carbanion is more stable than the tertiary carbanion. So formation of product will depend on the ring opening, and ring opening will be based on the stable carbanion formation. That's all about this particular rearrangement. Thank you for watching.